All right, here are your notes on section 5.3. Okay, so satellites and celestial bodies in circular motion are really what we're looking at is Kepler's three laws. Okay, and so just a couple scientists that we're going to be looking at really, Tycho Brahe is the one that kind of started looking at celestial bodies and things. Johannes Kepler is the more famous one we've probably heard of before. He's the one that discovered that planets actually are in ellipses instead of circular motion as far as around celestial bodies. Like, so we go around the sun in an elliptical and so on. He used a lot of Brahe's stuff, and so we like to recognize him too. Okay, and so Kepler came up with the three laws. Basically, and again, it's a very exaggerated ellipse. Really, it's really close to a circle, just a little bit off. But to kind of understand kind of what we're going to be working on, it's good to kind of think of it as more of an oval. So all planets in the solar system have elliptical orbits with the sun at one focal point. Okay, and so again, like we have two focal points here. Okay, so like this would be like it'd actually be in our summer. We're further away from the sun, and then as we get closer, it depends on the tilt of the Earth always too. And again, this is really exaggerated. Okay, but we have these different. We have the major axis, the semi-minor axis, the semi-major, and then the minor axis going up this way. Okay, and we'll talk about those kind of and do examples of those. Well, all the examples today are out of your textbook, so feel free to read over and look at them. If you need more examples, just let me know and I can do some. Okay, so Kepler's second law, is a line drawn from the sun to a planet sweeps out equal areas in equal time. So basically what it's saying is like the area here is equal to the area here. So area 1 is equal to area 2. But because the 2 is so far away, like it's stretched out. So basically the Earth has to get from this point here up to this point here in the same amount of time that it has to go from here to here. And so that's going to be helpful later when we're talking more about Kepler's laws and do an example. So in order to do that, okay, if we look here, it has to go a lot faster to get from this point to this point than it does like this. It has less far to go, so it doesn't have to go quite as fast. So this kind of law, by knowing that it has to kind of get from here to here and here to here in the same amount of time, it makes sense that our planet does not stay at a constant speed in its orbit. Depending on where we are in the orbit, it's actually going to slow down or speed up because it has to cross that in an equal amount of time. So Kepler's third law is kind of to help us understand that. So the ratio of a planet's orbital period squared to its orbital radius cubed is a constant. So all planets orbiting the same focus, so like the same, so in our case, like all the planets orbiting our sun have the same constant. Okay, and so the way that we can kind of get this is, so this is time or period, I guess, is capital T, okay, over radius. So the time or the period squared over the radius cubed is equal to k, which is just a constant. Again, it all have the same constant. Okay, if we're comparing between two different kind of celestial bodies, we could say like the period of A squared over, or the radius of A squared is equal to the period of B squared over the radius of B squared. And so here's just showing, and the Kepler's constant, I believe, is in your data sheet. It is no, it's not on your data sheet. All right, so but we can solve for, I guess it changes depending on the celestial body that they're going around. So, okay, the distance from the Earth to the Sun is often expressed as 1 astronomical unit. Again, so that we could use as a radius then. And so different planets, okay, so this would be their Kepler's constant for each of them. Okay, this is the period that they go around the sun. So like for Earth, 1 year is how long it takes us to go around the sun. Okay, and then their semi-major axis in meters. Okay, this is in meters, and all of these are times 10 to the 10. And so if we're doing an example like with Mars, okay, this is in your textbook. Oops. Just gonna pause the video for a second here. Okay, so this is on page 272 and 273 in your textbook. So it's just looking for like what if we know the radius of Mars, okay, what is the orbital period? Okay, and so you'd use k equals t squared over r cubed, all for Mars. Okay, we know we want to rearrange that to solve for t. So it would be the square root of k times r cubed. Okay, you can find the k value on another page, or like it's in your textbook. Okay, but basically you got 1 area squared over au cubed times 1.5 au cubed, and you get your area, you get your time 1.87 a, so like 1.87 Earth years. Okay. This is in your textbook on page 273. Just kind of some key points you need to know. It's also, it is on your data sheet on the back page, just under celestial constants. Okay, another example of your textbook on page 275. Okay, and so just this one talks about Mars. It has 2 different moons. Each one has a different orbiting radius and orbital period. If you're given one radius and period, you can find the radius of the other if you're given the period, or if you're given the period, you can find the radius. And so you're just rearranging. Basically, the formula you're going to use is t squared of the one moon over r cubed of the same moon is equal to t squared of the other moon, in this case Phobos, over r cubed of Phobos, and then rearrange. In this case, we want to find our radius of Deimos, and so it'd be equal to t squared times r cubed, t squared of Deimos times r cubed of Phobos divided by t squared of Phobos, and then you'd want to use the cube root on it. Okay, and again, all of these, like they're written out, these examples in your textbook, refer to them, check what they look like. Again, I can do more. I can show you examples straight off your work if you want. So Newton's version of Kepler's first law. So again, Kepler came up with these 3 laws, but really a lot of what the work and the math he did was actually wrong. And so it's kind of like, and some of you have probably done this before, where you do all the wrong work but still end up with the right answer. They found out his laws were right, and that all worked out, but his math wasn't quite. So Newton kind of took some of this and revised it with the proper math. So Newton recognized that the force that caused the apple to fall to the ground is the same force that causes the moon to orbit the Earth. Okay, and we talked a little bit about this, like in our circular motion. Okay, again, when you think of like the velocity is tangential to the circle, okay, and then our acceleration is always towards the middle of the circle. So again, that would be our g. So basically, we can determine the speed of satellites, so in this case the moon, if we know certain things about the Earth. Okay, and so because we know, again, centripetal force is equal to the mass of our satellite in this case, so the moon, times v squared over r, and that's going to equal the force of gravity that's pulling it in. Okay, so the centripetal force will equal the force of gravity, and we can find the force of gravity, which we learned in the last unit, is equal to capital G. That's a constant. Okay, that's in your textbook. That's the gravitational constant times the mass of the moon times the mass of the Earth divided by r squared. If we want to find the speed, we rearrange it. Okay, if we divide both sides by the mass of the moon, they end up crossing out. And then same if we divide or like bring this r, this keeps coming up, but if we bring this r up, it's going to get rid of one of these r's. Okay, and then we're going to square root the whole thing. So, so the mass of the moon cancels, one of the r's cancel, and so this is our rearranged formula, and we get the velocity. If we want to know the velocity of any celestial or satellite, it's just going to be the gravitational constant times the mass of our satellite, or sorry, mass of the whatever it's going around, so in this case Earth, times the radius between the two. Okay, and so an example out of your textbook. Okay, this is on page 278. Okay, and just showing like we're given the Earth's moon is 3.844 times 10 to the 5 kilometers from the Earth. Determine the orbital speed, okay, of the moon. All right. So pause this, please. All right, so measuring orbital height of a satellite. So usually, like when we're talking about how far satellites are away, like when we just did the measurement here, we were talking from the center of Earth. But usually what we're given is from the surface of the Earth. Okay, it's a lot easier to visualize. So, I'm not sure what's happening. And so, yeah, like we want to know how far off the Earth is the satellite. Okay, and so the orbital radius must be measured from the center of the Earth. Okay, but then we can find how far it is off the Earth because we know the orbital radius and we know the radius of the Earth. Okay, and so there's an example on page 279 kind of showing this. For this one, yeah, like again, like you find your radius, okay, from the center of the Earth, and then you need to use like the total distance from the center of the Earth to solve like when you're putting it into like the R skew or R formula. Okay, and then yeah, determining the mass of celestial bodies. So some of you have probably had this question before, like how do we measure the mass of the Earth? Okay, you can't just take the Earth, put it on a scale or anything like that. And so really when we're measuring the mass of the Earth, we're using a lot of different formulas that we've used in the past. So our formula for FC, our formula for FG, again, making them equal to each other. So instead of using the formula with V in it, like we did earlier, now we're using the formula. So for FC is 4 pi squared m, and this is the mass of the moon times r over t squared of the moon. So the time it takes for the moon to go around the Earth. Okay, is equal to Fg for the moon and the Earth. Okay, if we make them equal to each other, rearrange, we can solve for the mass of the Earth. Again, the mass of the moons cancels out. Okay, and so this would be our formula to find the mass of the Earth. Okay, and we could do the, like, so as long as you can always measure the mass of whatever's the larger mass that the smaller one goes around. Yeah. And so yeah, the masses of moons cancel out. Okay, and then orbital perturbations. It's basically an irregularity or disturbance in the predicted orbital of the planet. Okay, and so like the planet Neptune was discovered through the observation of orbital perturbations. Okay, of the orbit of Uranus. So they kind of knew where Uranus was, and based on kind of looking in the orbital perturbations, why it would act that way, there's some force of gravity between Uranus and Neptune, okay, and that's gave away that there's a planet there. Okay, and then geostationary satellites. Okay, so basically, geostationary satellites orbit the plane of the equator with the same axis of rotation as the Earth. So they stay kind of around the Earth over one spot on the Earth the whole time as it goes around. A geostationary satellite always stays above the same point, or it's also called a geosynchronous satellite. Okay, so its period is equal to its period of revolution is 1 day because it stays around, like the Earth turns over 1 day, and so it stays around that same point the whole time. Okay, again, look through these pages in your textbook, so page 269 to 286, especially like using those examples, okay, as you're working through the problems. Okay, and if you have any questions or anything, feel free to email me. We'll do a Google Hangout tomorrow based on your assignment.